We were talking about enthalpies and standard enthalpy changes last week. And this week it's time to discuss each of these standard enthalpy changes very fast so that we can start Hess's law, which is the important aspect in this chapter. So let us start with the enthalpy change of a reaction. A very important enthalpy change. By the way, every time we have this sign from now on for enthalpy change, we'll mean the standard enthalpy change so that we don't write all the enthalpy change of reaction, for example, like that. Because this symbol here, it's quite hard to write and takes a lot of time until you write it. And that's why I have omitted it. But we are talking about always, we refer to standard enthalpy changes. So what is the standard enthalpy change of a reaction? Is when we have a chemical reaction, any chemical reaction, it's the enthalpy change of each of these reactions. These are two examples, the composition of calcium carbonate and what is the combustion of methane. This number that we see here, these values that were given represent the standard enthalpy change of these two reactions. For the top one is a positive value, which means that this reaction is endothermic, as we have seen before. And this one is an exothermic reaction. Obviously, it's a combustion reaction. It's an exothermic reaction. Therefore, the standard enthalpy change is a negative value. So, in general, the enthalpy change that occurs when the amounts of reactants shown in the reaction equation, react to give the products shown in the equations. So, why do I make this big fuss? Is because the standard enthalpy change of a reaction it's a value that corresponds to this particular reaction. We don't have to discuss formations of or amounts of reactants of or products in terms of how many moles of this and that we have. It just refers to the whole of this reaction. So when we see this value here, this value corresponds to 1 mole of calcium carbonate producing 1 mole of calcium oxide and 1 mole of carbon dioxide. Whereas here, in this second reaction, we have, this is the value of the enthalpy change when 1 mole of methane reacts with 2 moles of oxygen and produces 1 mole of carbon dioxide and 2 moles of water. So we see here we have different amounts of moles. We have both single moles and double moles in this reaction. So when we see enthalpy changes of reaction in problems, they will usually tell us, if necessary, the moles that are involved in the, whether they refer to particular moles of a particular product or a particular reactant. Anyway, let's go to the next type of enthalpy changes. Here is another important enthalpy change, which is the standard enthalpy change of formation. Again, we're talking about the standard enthalpy change of formation, which is the enthalpy change that occurs when 1 mole of a compound is formed from its elements. So from now on, from all the other standard enthalpy changes that we're going to meet, we are told 1 mole of what is going to be involved in this standard enthalpy changes. So for formation, for example, let's see, I'm looking at your book now, standard enthalpy change of formation. They have a number of examples here. For example, let's look at this reaction. We have iron metal reacting with oxygen, 1.5, it says, 1.5 oxygen gas to produce ion oxide of this type. Obviously, this ion involved is the one with valency 3. That is why we have this, the formation of this. The product is this oxide, ion 2, oxygen 3. Anyway, this is 1.5. This is how it is shown in your book. And it says here, let us be careful what we are talking about here. The enthalpy change that occurs when 1 mole of a compound is formed. Here is the 1 mole of the compound that is formed, okay? So if this is 1 mole, then the enthalpy change of this reaction is given as, a formation of this compound. The enthalpy change, the standard enthalpy change of formation in this case is a negative value. It's minus 824 kilojoules per mole, of course, kilojoules per mole. And that is why they have written this equation in terms of 1.5 here, which is funny to see an equation of this sort. But the thing is that this value given to us corresponds to the formation of 1 mole of iron oxide. If we had written this this reaction differently to get rid of these fractions, because we said usually by convention we write chemical reactions to have coefficients which are whole integers. This should be properly written as 4 ion atoms solid, plus instead of 1.5 we should have 3 here, oxygen molecules, gas, and that would give us 2 moles of iron oxide of this type. This would be our proper equation, how we would write it in chemistry usually. But then we should pay attention. If they were to give us the enthalpy, the standard enthalpy of formation of iron oxide, that would be for 1 mole, and they don't want us to get confused. So the enthalpy change of formation of minus 824 kilojoules per mole, this value represents the enthalpy when 1 mole of this compound is formed, not 2. Here we have 2. So if we were to use this equation in our problems, we should be very careful to divide our values by 2 so that we have the correct value for the correct number of moles, okay? So I hope this makes sense. Emma, please tell me if you understand what I'm saying there, because this value corresponds to the enthalpy change per mole of compound formed, okay? And, so let me see. Okay, good. So, all right. Now let's go to another enthalpy change, standard enthalpy change, that of combustion. Again, this is a standard enthalpy change of combustion, and we symbolize it with a C here for combustion, much as this one should have a little f there to say standard enthalpy change of formation. This is for combustion now. And again, we have to be very careful. The enthalpies of combustion, the combustions that we are going to be given represent the enthalpy changes when 1 mole of substance is burned. The burning substance, for example, any equation of combustion, let's see, what do they have here? Standard enthalpy. Oh, they have the combustion of sulfur and the combustion of methane. Let's write the combustion of methane. So let's say methane plus oxygen, since it's a combustion, of course, that the product of combustion is carbon dioxide and the water. Now we have to add the states. This would be a gas, of course. This is also a gas. Carbon dioxide is a gas. Water could be liquid usually. Sometimes they give it to us as a vapor, but fortunately here they give it to us as a liquid because water in its standard state is liquid. So let's see now, 1 carbon, 2 oxygens, 2 and 1 3. Okay, we need to put here 2 waters and here 2 oxygens to balance it. I hope it's balanced now. Yeah, it's balanced. All right. So 1 mole of substance is burned. Which substance we're talking about burning? This is the substance burning. So, okay, fortunately in this equation, it's already 1 mole, so we don't have to divide with anything to change into 1 mole. And the standard enthalpy change of combustion of methane is given to be minus, obviously it has to be a minus value since it's a combustion, it's an exothermic reaction, 890,3 kilojoules per mole. So this value that we are given for the combustion of methane is the correct value if 1 mole of methane burns. If it so happened that here the coefficient was not 1 but something else, we could divide all of them with the correct denominator or whatever, so that we have 1 mole, so that this value here corresponds to 1 mole of substance burning. Okay, so 1 mole of substance. So every time we have one of these standard enthalpies of combustion, we need to know what mole they are talking about, because there's always per 1 mole of this and that. Let's see another standard enthalpy, that of neutralization. So in this case, we could symbolize the standard enthalpy of neutralization, maybe with an N here to say neutralization. So this is now the enthalpy change that occurs with 1 mole of water is formed from the reaction of an acid and an alkali. Because neutralization is usually when we have an acid and a base reacting, and the result is always a salt and water. But of course, these are now, this type of reactions of neutralization usually happen as aqueous solutions. And so let's just write a reaction like that. Where are we? Neutralization. Here we have hydrochloric acid reacting, hydrochloric acid reacting with some base, which is sodium hydroxide. Now, because the base is aqueous, it's in water, in solution, we don't call them base, we can call it goodness. Alkali. What a difficult word to remember. Alkali. So when we hear alkalis, the word alkali means that it's a base in solution, in aqueous solution. That's why it's called an alkali. So in other words, all alkalis are bases, but not all bases are alkalis, as you probably know already. So okay, we have hydrochloric acid and sodium hydroxide, and of course that will give us some salt, sodium chloride, and water. Okay, now because these are all aqueous solutions, we have to put the states here: aqueous, aqueous. This is also aqueous, and water, of course, we say liquid. So you see where the water comes. Hold it, is this balance? It is, yeah. So there is an example of a reaction, a neutralization reaction, and they say that the enthalpy, the standard enthalpy of neutralization, in this case, which do we have a value? It's minus 57,1 for this particular neutralization reaction, kilojoules per mole. And this value now represents the enthalpy change if 1 mole per mole of water that is produced. Okay, here we have 1 mole of water produced, so this this value corresponds to this reaction where 1 mole of water was produced. If there was more moles of water produced, obviously, we need to remember in problems that this value if we take this value from tables, corresponds to the production of 1 mole. If there were more moles, we should have to multiply, obviously, this value so that it corresponds to the correct amount of water produced. So the enthalpy change that occurs when 1 mole of water is formed from the reaction of an acid and an alkali. Okay, so similarly, we have standard enthalpies of solution when it's the enthalpy change that occurs when 1 mole of solute is dissolved in solvent to form an infinitely dilute solution. And then the standard enthalpy of atomization is when 1 mole of gaseous atoms, 1 mole of gaseous atoms is formed from its element, and so on. So always we need to be aware of what mole this energy, that this enthalpy change corresponds to 1 mole of what, because sometimes this mole concerns something from the reactant, sometimes it concerns something from the products, and we must be, that's the only difficulty in other words, to be very careful of what mole of whatever compound is they're talking about. So you see, there is no need to do to go in details in each one of these, because we're going to see them again and again in the future. Just to have an idea that there's always this value that they give us of for the enthalpy change corresponds to 1 mole of something. That's the only difficulty, to know which mole we're talking about. Here it's 1 mole of solute, here is 1 mole of gaseous atoms, and so on. Because I would like us to, oh dear, it's already 11:55, of course. Because I would like us to go straight to Hess's law. And considering we don't have enough time now, maybe we should go to Hess's law next week, and maybe we should discuss this with some more examples then. So the enthalpy change, the standard enthalpy change of solution, the standard enthalpy change of solution is the enthalpy change that occurs when 1 mole of solute is dissolved in solvent, enough solvent that is, to form an infinitely dilute solution. So where is the solution here? For example, when we dissolve sodium hydroxide in water, we add sodium hydroxide in water to produce, so the sodium hydroxide, I mean, usually it's a solid, okay. Now, if we add this in a solution, and because we add it in a solution, in a solvent, actually, in a solvent, usually water, we add it in water, they symbolize it with aqueous, means in water solvent. And the result of this is that the sodium hydroxide becomes aqueous because it's now dissolved in enough water. We're talking about aqueous solutions. Eh? So 1 mole of solute, what is the solute here? This is the solute. So we need to have 1 mole of that. If we have 1 mole of solute added into sufficient water, then there is a change in enthalpy, this one, and in this case, they don't give us a value here. All right. But nevertheless, there is a change in enthalpy even when we dissolve something in water, even then, which is not, strictly speaking, a chemical reaction as we know them, although this one dissociates in its ions, but there is an enthalpy change. And in this chemical process, this enthalpy change is called the enthalpy change of solution. And usually we need to have enough water so that this solution is kind of infinitely dilute, so that if we add any extra of the solute, there's no extra change in the enthalpy change of a solution. Another thing, okay, one thing, we must not confuse enthalpy changes of solutions with enthalpy changes of hydration, because the enthalpy change of a solution is when we add a solute in enough water. But the enthalpy change of hydration, I don't know if you're familiar with this, the standard enthalpy change of hydration. This represents a different type of reaction, hydration, where it's not a matter of dissolving. The enthalpy change of hydration is when some salt usually reacts with water and produce a hydrated salt, which is solid. It's not a solution. For example, here they have sodium thiosulfate here. Let's see this reaction. Let's write down this reaction. This is this funny compound, sodium thiosulfate is called. It doesn't matter how it's called, but nevertheless, this compound now reacts with water, five molecules. 5 moles of water react with 1 mole of this sodium thiosulfate, and the result is it produces this hydrated compound, which is this is now solid. This water here is supposed to be liquid, of course. So the formation of this compound, this hydrated salt, is a solid. It's not a solution. Okay, so these two are not the same thing, because this word hydration might fool us into thinking that we have liquids here forming or solutions, but it's not. Okay, so the standard enthalpy change of hydration is when some salt or some compound changes into a hydrated compound. In this particular reaction, the enthalpy change of hydration is given the value of minus 55,0 kilojoules per mole, and this value, this represents the enthalpy change when 1 mole of hydrated salt is formed. So this is the hydrated salt that is formed, and this is the 1 mole that they're talking about here. This is the 1 mole of hydrated salt. So values for standard enthalpy changes of hydration correspond to the formation of 1 mole of hydrated salt. So we must be very careful that here we have 1 mole. If we have other coefficients here, we need to convert as necessary in the problem. What else have we left here? The atomization. Actually, this is quite an interesting reaction here. Atomization, quite useful that is. Which is the enthalpy change. Oh dear, it's past 12. When 1 mole of gaseous atoms is formed from the element. So let's say we have hydrogen, for example, gas. If it changes into atoms, also gas, hold it now, because here we have to add the coefficient of 1/2. So this energy change of atomization, standard enthalpy change of atomization, in which case is 218 kilojoules per mole, corresponds to the formation, this value corresponds to the formation of 1 mole of gaseous atoms, 1 mole of this, in other words, 1 mole of gaseous atoms. That is why they have written the equation in this form with a fraction here.